epoxys. So I will share my screen. Can you see my
Yes.
full screen?
Yes.
Yes, okay. So thank you also all for joining. This is the plan of my presentation. So I wanted to start with a few words about my background and epoxys, but you already presented a lot. I always start my presentation with holistic considerations about the energy transition to put the context, the general context of energy transition and how geothermal, deep geothermal could help. Then I will present deep geothermal systems from conventional technologies to geothermal anywhere, so from hydrothermal systems to petrothermal system, which are harvesting the heat directly from hot, dry rocks. Then a few slides about our roadmap, how we structure our development around our EPO Lab initiative, which is an open lab initiative. And then finally, low-hanging fruits, how can we accelerate the deployment? So for the background, it has been said, so my background is in geoscience and geophysics. Since 2017, I'm the co-founder of epoxys. We started the project from a blank sheet, asking the question, how can we make geothermal anywhere without the need for fracking? And the reason for that question is probably because being sited in Switzerland, where we have two deep geothermal projects that have been aborted because of induced earthquakes that were widely felt by the local population, it makes sense to, I mean, we have strong opposition from the local population. This is still the case today. There is an enhanced geothermal project that has been planned for years, and last week they have encountered like demonstration as they are starting the exploration drilling phase. So it really makes sense here to try to make geothermal without fracking. And so it drives you to the only solution that is actually how to construct a deep radiator to extract, harvest the heat stored in deep hot rocks. Maybe a word on the other co-founders also who you can find on the web page, but there is Patrick Scherer, who has joined also the webinar. He's by training a political economist, computer scientist with a vast experience in venture capitalism, and so he's really helping on corporate strategy, because this is not something that you learn in the university, I would say. And the other person is Lucien Vouillamot. He's my father with a training in nuclear engineering physics, so specialized in heat exchanger system. But he has had like an unconventional curriculum. He has been a missionary, and then he came back. When he came back to Switzerland, he started to make new companies based on innovation, and so he gained a lot of experience in patenting. So this is his role in the company, is making sure that we protect what we develop. I also wanted to say a word, maybe to give the general background. My aspirations are really concerned. I really consider myself as a concerned scientist. I have two children. I don't want them to come to me one day and say, hey, as a nurse scientist, you saw that coming and still you continued with business as usual. So I want to avoid that situation. I have done 3 years of politics. I resigned from my seat early this year because I think I found it too slow. And so I would say I'm back to pragmatic environmental activism. I want to transform, I want to move things. And this is why I engage myself really for a fair transformation of our society towards less ecologically destructive lifestyles and also less inequalities, I would say. This is what is important for me, and I have illustrated this with two pictures that tell good how I feel about the situation. Next slide. So, the holistic considerations. I would say, I think our civilization is facing a global and systemic crisis, and one aspect of it is found at the energy-climate nexus. And I'm trying to illustrate this with a triptych slide going from the left, so our carbon budget. This shows you that basically the 1.5 degree budget is exhausted. This target is dead. But what I also wanted to emphasize here is the mismatch between, I would say, what is being said and what is actually achieved. Environmental concern has been out there for a very long time. I have put one date here, 48, Our Plundered Planet. This is a book that has been published in the US, raising alert on the fact that our civilization may be impacting the environment too much. In 72, you have the Stockholm Conference, which stay at the origin of the conference, the IPCC and the conferences of the parties, where we invented the concept of sustainable development, actually. And this is how it goes until 2015, where thank God we have an agreement. And in not even 9 years, I mean, we have managed to release 20% of the full budget. So quite crazy the speed at which we miss the target. And then the question is that going beyond this budget is our inhabitable planet going to enable us to be living on it? This is what we are actually talking about. And the IPCC, the sixth assessment report, they have released many different projections to show how this may look like. And I have selected just one of these projections showing the number of days per year where the cocktail of heat plus humidity is deadly, because it's too hot and there is too much water in the air, so you cannot sweat to cool down and you die. So now I think most of the people don't want this to happen. And this is what I call the issue, is that we actually know pretty well what we are supposed to do, is that we should leave most of the fossil reserves untouched. This is taken from a Nature publications from 2021. And obviously easier said than done, because our whole economies are related, are coupled to the fact that we consume fossil fuels. And so this is why I think we need a plan, and a serious plan. And I believe that deep geothermal could be a serious element of this plan. So the question is, how can we realistically phase out fossil fuels? And on that side of the slides, of the graphic, what I show is the historical consumption, the global historic consumption of energy. And I think it illustrates very well that we are an oil, coal, gas civilization. I mean, we burn fossil fuels in addition to wood, which we have never stopped to burn. And the question is, how can we go out of that? And here on this slide, on this side, so I have copied the emission reduction slope to keep global warming below 1.5 degrees. So it's pretty steep. I'm not saying that we are going to be able to reach this, but what I would like to say is that geothermal, and especially deep geothermal, has a very elegant card to play in that, because it could add a new form of energy. Deep geothermal energy is available everywhere. It is low carbon, it is local, it is sovereign, so it belongs to the people on top of it. It is baseload, it doesn't depend on meteorological conditions or seasonal variations. It has minimal land footprint. If compared to wind and solar, I think it's between 70 and 90% less per kilowatt hour produced. The assets are underground, so, and this I think is becoming more and more relevant. I don't know if some of you have seen the amazing footage of the tornado last week in Iowa in the US, where you see a field of wind turbine being like blown up by the tornado. So the fact that the infrastructure is underground is a very good point for against extreme weather events, which are becoming the new normal. And you can use deep geothermal energy to supply heating, cooling, electricity, so pretty much everything we need. Now, what I think is very interesting is that it could be used to de-escalate oil and gas by pivoting the oil and gas industry into geothermal, by taking the rigs from the oil and gas industry to start to drill to produce the heat instead of drilling to produce oil and gas. Yeah. Now, I think another aspect where geothermal is very interesting is that the energy transition, I think something that is very often overlooked in the energy transition is that it adds reliance on the mining industry. On this periodical table of the element, you see it's a qualitative representation, but you see the spread of what we actually call clean energy technologies. And so it's really the situation that the current trends in energy sustainability agenda are posing a serious pressure on the metal demand. And this means that there is a risk for critical resources depletion, critical resource becoming a strategic resource. So you can have the effect of geopolitical conflicts, supply chain instabilities, fluctuating pricing, and this is not even talking about the fact that the mining industry is the most polluting industry. No contest. It is the biggest, it is responsible for the biggest amount of solid liquid gas toxic waste worldwide. It doesn't perform well without cheap and abundant access to fossil energy, and it is very controversial. So in that context, deep geothermal, I think, can help because it has lower critical metal dependency. It is actually an important consumer of steel and cement, but which are still locally available. So it could be used to revitalize our local industries, provide employment. And one thing I believe also is very important is that it's about relocating the environmental externalities. And I'm pretty sure that when you have the installation deployed next to you, you will take care, you will make sure, you will pay attention on not having too much pollution or so on. So, deep geothermal also, as a reminder, is tapping into the Earth's largest energy source. I mean, the deep heat of the Earth represents a much larger reservoir of energy than fossil. The only difference is that it's less concentrated, it's more diluted, but this could be, if you think about it, compensated by the fact that you will make a direct use of energy on site. There is no need for long distance transportation. complex refinement. I mean, it's direct available for use. Now, when we speak about deep geothermal system, I really think it's a spectrum of application. So I'm not talking about heat pumps. I'm also not talking about traditional geothermal installations sited on volcanic areas where you have access to hot fluids very close to the surface. It's really the geothermal system that will harvest the heat gained by the geothermal gradient. So starting at a few kilometers depth, and the application is for heating, cooling, or electricity generation if the temperature is high enough at the community level. So the capacity of the system, I would say, is in the megawatt thermal range for one inlet, one outlet, or one doublet. Then you can specify the type of application. So you have the hydrothermal application, which I would say are constrained, so limited by the fact that there is a need for a hot permeable aquifer in the underground. And the figures I've taken here, so the 0.01% and the 99.99% come from a publication, Brown et al. 2012. I'm not saying these numbers are exact, but I think they give the order of magnitude. And I think this is a very clear argument to say that if we want to scale geothermal to a significant contribution of the global energy mix, this is not an option. We will have to develop geothermal anywhere application, so the petrothermal application. Now, on the design, you can split between open loop system and closed loop system. I would say the open loop are the conventional or enhanced, where you will produce brines. The heat recovery is a faster process because it's advection, convection, so you could expect higher capacities for the system. But you have the risk for induced seismicity, especially for the enhanced. The technical challenges are mostly on permeability management, the pumping, corrosion and scaling, because you have to deal with the local geochemistry. And the power output is, I would say, more difficult to control, and it's more like the nature will define the power that you can get out. For a closed loop system, you control the working fluid. The heat recovery is by conduction only, so it's a much slower process. But it also means that the system can be designed for the very, very long term, because you will not deplete the resource. There is no risk, I would say, for induced seismicity because it's pressure balanced. The technical challenge is obviously long, deep directional drilling, because you rely on conduction only. So it's the only way to increase the contact surface is by drilling longer and deeper. But a big advantage is that it is predictable and tailorable. That is, you can design the system to the exact size of what you need. So at IPOSIS, we are developing the last application, so the advanced geothermal system, multiple leg closed loop. I have put this name, incremental multiple legs closed loop AGS. It's an awful name. I'm aware of that, but I think it describes quite specifically what we are doing. So at IPOSIS, what we want is that we own the design. So we have patented the architecture and the service well that we use for incremental drilling of the deviated well pairs. So if you see my mouse from here, that we connect to the injection and production wells, then we disconnect from the service well, and we have a first loop that we call an IPOLAP. And what we claim is that as soon as we have the first IPOLAP completed, we can start operation and start generating revenues. This may present an advantage if you think in the context of deploying a district heating network, which is also often a staged process. You don't open all the sectors at the same time, so it could make sense to have a staged or a phased increase in capacity of the system. The environmental advantage of the closed loop, it's reduced fluid needs. There is potential for standardization, no power loss for pumping because of the thermosiphon effect. Because we have no use of fracking, the system can be deployed very close to community, and this has an impact on the fact that you can really optimize the energy return on energy invested by being as close as possible to the consumer, and really design the system at the exact size of what is actually needed. On the economic side, because it is conduction only, it means you can predict the energy output very closely over the 100 years to come, and this means also that you can have stable energy prices. However, because of the long drilling required, it comes with high upfront capital, but for this, we also see this actually as an opportunity because it enables the development of new long-term financial model, which could actually help to capture all the money that is floating around in the financial space and bringing that to the real economy and to long-term infrastructures. So EPOSIS is really, it represents a tailorable system, deep geothermal closed-loop solution to empower communities with managed risk, predictable performances for very long-term energy supply. This would be the take-home message. Now about our developments. We are structuring these developments on like 3 pillars, which are rooted in what we call the EPOLAB initiative. The 3 pillars are the one for that we call EPOLAB. It's AGS, I would say, construction technologies. So it's really about the deep drilling, identify, develop the best drilling and subsurface solutions for the AGS. Then we have the EPOSIM, which is our software platform to optimize or maximize the energy return on energy invested and the life cycle impact assessment. So it's really about getting the best dimensioning of the system in any geological or social demand context. And then we have the EPOFIN, which is about, I would say, enabling a new energy economy. And we have, our compass is really that we consider energy as a common good, and all our development follow this guideline. And then the EPOLAB initiative is an open lab public-private alliance initiative because we certainly cannot do this alone, so we need partnership to cooperate with. Yeah, so I have one slide for each of these blocks. So for the EPOLAB, I would say drilling technology is here and only getting better. This diagram is not from me. I have taken the original illustration from Andreas Reinicke. He presented it at the Geothermal Transition Summit last year in Berlin. I think it illustrates so nicely all the development that are currently being pursued for improving deep geothermal drilling, so for achieving faster, longer directional drilling in deeper, hotter, harder rock. This is the objective. And what you see here on the left is I would say, the fine-tuning of conventional drilling with already some amazing results achieved at scale. I have put some references down there. And the blue part, I would say the non-mechanical, is the field for potential disruption, but the technical readiness level is not that high. Now, we are not, Eposys is not a drilling technology company. So we want to select the best available technologies. And for the first pilot, we want to use off-the-shelf drilling technologies. So we want to make our first site with existing technologies, but then, of course, we would also like to drive new drilling specifications for better performances. And this is also why we keep close look and we follow very closely the developments here, because we want to be ready when they are ready. Then for the Eposim, this is really about designing, like I said, the best AGS layout for long-term energy supply. And so for this, we have a series of analytical calculation tools that are developed by Professor Pierre Perrochet. He's just got retired from Neuchâtel University, the Center for Hydrogeology and Geothermics. And the general principle that we have in these tools is that we start with the Eposys generic layout. So it's a series of polygonal lines that are simply described by their geometries. And then the objective is to play with that. So there is a term that enables also to take into account the thermal influence between different wells within the geothermal field. And the idea is then to combine, so vertically, for instance, but then also horizontally, because there are many different geometries that are possible with the service well. And with that, we try to get out in a systematic way some important parameters like the total length that needs to be drilled, the maximum flow rate that you will be able to put in your system to sustain output temperature that remain above 70 or 120 degrees Celsius over the very long term. 70 degree would be for district heating application and 120 for electricity generation application. Then the related power output in megawatt. And what we try to maximize is this, so it's the linear maximum flow rate and the maximum linear power output, so the megawatt thermal per kilometer drilled. I have just provided here the kind of abacus we can take out. This is the simplest system actually. So a single loop with one injection, one production, and one production well, and the maximum temperature is set, so which gives you also the maximum depth, is set as 175 degrees. And what you see is that with a single loop, you cannot sustain temperatures above 120 degrees Celsius. If you don't make any tricks, you will not be able to generate electricity. But for heating would be okay. But so I have like summarized in the table here, I would say order of magnitudes of what can be reached. For heating application, you can put higher flow rate in the system between 1 to 1.5 liter per second per kilometers of laterals. And this will give you 0.2, 0.3 megawatt thermal per kilometers of lateral. I insist, for the very, very long term. So we look at 100 years plus. And we have the parameters that are inside are standard parameters. So it's still very conservative values. A normal geothermal gradient of 30 degrees per kilometers, injection temperature 25 degrees, maximum 175. The well diameter is not a first order parameter in the sense that there is very small differences from wells diameter ranging from, I would say, 6 to 9 inches, you don't see almost no differences. And the completion at the moment is considered like barefoot for the EPO labs, and no installation on the injection and production wells. For electricity generation, because you don't want to deplete the temperature below 120 degrees, it means you cannot use the flow rate. The maximum flow rate is 0.5 liter per second per kilometer. And I would say the maximal thermal output that you can expect based on our calculation is 0.2 megawatt thermal per kilometer. And this gives you like this reference system size. So for heating, 25 kilometers of lateral deployed around 3 kilometers depth would be enough to produce 25 liters per second for 5 megawatt thermal. And for an electricity generation plant, it would be 50 kilometers of lateral at 5 kilometers depth, circulating 25 liters per second for 1 megawatt electricity. And if you look at Ever in Geretsried, this is pretty much the number that they have also for 1 unit. Now, about the financial aspect, I have taken this sentence from the Great Simplification film on energy, environment, and our future, is that in addition to using different energy, we will need to use energy differently. I mean, if we are serious about phasing out fossil fuel, there are a number of things that we will need to change. And this includes also the way our economies are functioning. I'm aware this may be a bit provocative, but it's the best way I've found to illustrate how I understand the situation, is that currently our economic system, we have an imperative for growth. And this comes with the result that we are using more and more energy and more resources. And a result, we degrade, we pollute, we degrade the environment. Now, we have been talking about decoupling GDP growth from fossil fuel or from environmental externalities for a very long time. And the fact is that this decoupling has not happened. And personally, I believe it will not happen. It is even worse than that. Current research papers are showing that we are actually having a surcoupling or overcoupling. So we use more, we mobilize more and more resources and energy to create 1 point of GDP. So our proposition at IBOSIS is to say we should turn this thing over and say the entry point is a rational use of energy and resources. And the economy is actually a fix. It's a tool that is at the service of the society, and it should not be the opposite. It's not us to be at the service of the economy, it's the economy to give a service to the society. And if we do that, I believe we may have a chance to preserve the environment. So what we implement in our development is really, we have this energy is a common good. It is not ethical to speculate on energy. And so if you consider energy as a common good, there are a number of propositions that come right away. I would say it's the concept of energy communities with energy at cost, increasing the energy autonomy, where geothermal could really help. And being autonomous means also supporting peace, because there is no reason to go to the neighbor and try to steal it away from him. We will need new behavior. I think there is a lot of innovation in social behavior, in sustainable lifestyles. And for this, we need new business models. And I have put on the side, it's not exhaustive, but it's a number of things. Tank Institute, Research Institute, or essays and publications, where I think they are proposing very good and meaningful ideas, and this is our inspirations, I would say. Now for the EPO lab, gathering the community, I have used the Yes We Can. I think it's really about the mood. We need to create the community to realize geothermal. And this is about cooperation. It's not about competition yet. So it's really about gathering the people that believe in it and that want to make it happen. And this is what we have initiated with this IPOLAB. We have released a white paper last year describing what we have in mind, and we have started to build partnerships and arrangement with other companies or research institutions to go in that direction. So the IPOLAB initiative is about a public-private alliance network with the objective to accelerate the adoption, but also to be able to transfer the learnings faster. We target in our financials, we target the deployment of 10 IPOLABs by 2030. It's very ambitious, but I think we have to be. And we see ourselves really as the catalyst. We have a non-vertical, a distributed business model that allows for a lot of flexibility. And so we think we should be able to cite different IPOLABs. So one IPOLAB is really an AGS pilot, a production site in a given country that comes along an AGS reference deployment guide. So in parallel of building the pilot, we want also to provide the reference deployment guide because energy is linked to the territory. So it comes with different regulations. It also comes with different energy transition targets, depending on the region where you are. And so we are at the beginning of that. I have presented here, I present the core partners. So we have been working very closely with well engineering partners. I would say they are almost us in the sense that they are the drilling engineer for EPOSIS. So they develop for us the well delivery sequence. And then beside this, we have also established the basis for a long-term partnership with Halliburton. We want them to be like the big ones, providing the credibility in what we do and also the execution capabilities. And then we are also working with Research Institute, Canopus. They are developing deep directional steel shot drilling. And we hope that we will both be ready at our next stage to work together. And yeah, also a bit of lobbying because I think it will be important. Now, about the low-hanging fruits for faster deployment, I really do see a case for enhanced geothermal system in the US and advanced geothermal system in Europe. In the US, they have a very ambitious strategy. They target 60 to 90 gigawatt electricity by 2050, and they have started to go for it. So they are investing quite heavily. There is the Utah Laboratory project in a space, Fervo Energy, with lots of very promising results. And I think in addition, it would make sense because they have all the shale oil and gas fracking industry, which might have less job considering that the Permian Basin is showing signs of depletion. So it would make a lot of sense to move this industry for enhanced geothermal system. In Europe, I think the people are against fracking. At least this is the case in Switzerland, I can tell. We have lots of existing district heating network, mostly running on gas. So it would be the perfect entry for AGS system because it's lower operational temperature and because AGS can be deployed close to community for lower operational temperature. We don't need to drill as deep. So it would also mean that it could be easier. And so I really think for me, like the natural entry market for AGS is the district heating network. Electricity can gradually increase. its share when we gain experience, because it's challenging to generate electricity with advanced geothermal system. And the last point is that basically heating is 50% of energy demand, so it's already a huge market. And I'm at my last slides. So for us, the next step, I would say, I cannot wait to escape the PowerPoint, get real. And what we have in mind is, what I'm showing here is the hydrothermal template. So this is an existing system, Rien in Switzerland, hydrothermal system deployed in Muschelkalk aquifer, so in the mid-Triassic age. It has been operating since 1987. One doublet deployed at 1.6 kilometers depth, higher geothermal gradient because it's in the Rhine-Graben. They produce 25 liters per second at 66 degrees with one heat pump, and this supplies 4.3 megawatt thermal. It's enough to supply baseload heat and sanitary water for 8,500 people. And here what I'm showing is the annual profile of the heat demand, where you see that really it covers, geothermal is the baseload component for a district heating network. So what we would like to do is replicate of that. At the moment, we have several discussions going on about potential locations, including in Norway, in Switzerland, some discussion in Turkey. And the idea would be to start with one injector, one producer, 2 EPO labs, so 2 levels, like I'm showing here, around 3 kilometers depth, and target 15 to 25 liters per second at 70 degrees, 3 to 5 megawatt thermal. Maybe start with a little bit smaller, but this would be the general objective. Baseload heat and hot water for around 500 people, 5,000 people, sorry. And I will close on that. Is for me what we should consider. I think there is really a need to change the way we talk about geothermal, about the risk and the technology maturity. And to explain myself is to say that basically AGS can be seen as a validated concept, because there is the Everlight pilot project in Canada that has shown that it's working. Now, the deployment is about technology transfer from decades of oil and gas subsurface experience. I mean, people from the oil and gas, I guess they know how to do that. And the optimization is just solving regular engineering problems, and this we know how to do. And I will finish on that. It's the time to go for it, and I hope I was able to convince you. So thank you very much for your attention.
Thank you so much. Thank you so much, Naomi.
Oh, Gabriel, hello.
I am here. Hello. Thank you so much for such a great presentation. It was very detailed and concise, and you brought up a lot of really important points, good points, not just technical per se, but mindset and what's currently going on in the world. I will tell you that I think we've hit a record in terms of the questions in the chat box, so I hope you have time. Let me know when you get to the limit, if the allocated time is not enough, but I'm gonna jump right into it.
Yeah, that's good. The only thing is that I might have my son coming back from school, but this is not a problem. I can manage both.
We appreciate that. Thank you, Naomi. Thank you. So let's get it started. So we got a first question. Well, before I get into that, I'd like to thank Marius for opening up the session and for supporting us. So Vincent says, hello, what is a typical fluid production rate and temperature? And are you thinking of using water or something else?
So at the moment, we have done all the calculation with water, but obviously we are thinking of using water plus some stuff. If you look at what Ever is doing, so they have like the rock pipe where they add some, I think, silicate, or I don't know what. The idea is that because you circulate a fluid, you also want the fluid to make sure that you will not have any loss. And so you should make sure that you have something that is like sealing the well. But at the moment, we don't have a dedicated composition. And to be honest, we actually consider approaching ever for their solution, because they have lots of patent around that. And our objective is also not to reinvent the wheel. If something is working properly, let's use it.
My user, yeah. Nice. So closed loop is not only has it started great, but it seems like the future is very, very promising. A question came from Joe Bami that says, what are the best working fluids for the closed loop?
Yeah. Again, I would say it's water plus silicate components, but there are also research on critical CO2. But this is at the, I mean, it's fundamental research. It's very promising in terms in theories, but then let's try it.
Yeah, I think they're working on it on small scale right now.
And then, yeah, you would have much higher flow rates for sure. Because with water, obviously, the closed loop, it's about circulating. This is the numbers I have put on the table here. It's like 1 liter per second per kilometers of drilled lateral. It's very, you should go very slow to make sure you harvest the heat out.
All right. So we did have a question that came in, and I think you've answered this already, about what was the maximum power generation expected. I think you already tackled that, but the cost for drilling of one system, I'm not sure, was that mentioned?
No, I didn't mention. At the moment, we consider installation around. So in our financial, we have considered reference installation costing 150 million. This takes into account quite conservative rate of penetrations. But still, I mean, if you look at the numbers, drilling 50 kilometers of lateral, it's a big number, huh? Make it clear. But then this is also what I tried to address. It's about changing the conception of the financial model. It's closed loop is long-term. So it means your installation is there forever. And when I say these numbers, this is really, I mean, you can sustain this for the thousands years to come. It's really on the asymptote of the curve. I mean, you are taking what's coming out, so you are not making heat mining. So this is what needs to be implemented, is that it is a long-term energy infrastructure that will deliver and supply energy for the decades or centuries to come. And this is how you need to balance the price.
All right. Well, I think just to make a comment over there, when you talked about drilling, I mean, look at what Fervo did in the United States. They started drilling the wells, and the improvement in terms of drilling time and efficiency is just, it's great, right? In such a short time period. So obviously, as I put in more efforts and innovation, I think some of these challenges will be overcome. Yeah,
and for sure, if you consider that you could imagine like regions or cities where you deploy like several units, and you would benefit definitely for this from this learning curve. So the first system will cost a lot, but then you learn, you understand the subsurface, and you go for it.
All right. So there was another question from Joe Bami that came in, and he asked, what is the approximate distance between the laterals to connect the two wells?
Okay. The vertical is, we consider about 75 meters, but then between the service well and the connection here, at the moment we consider up to 4 kilometers. This is the maximum, but for the first pilot, we are more like in the between 2 Yeah, 1.5, 2.5 kilometers, pretty much like ever, actually in Geretsried, where they have 2.7 kilometers, I think, of lateral. We don't want to push it too far at the beginning. But then there is the question that you could actually imagine, this is what is illustrated here, that you could combine and actually increase the length of the lateral by playing with the arrangement of the lateral between the injection and the production well.
Gotcha. Then Jos, and I hope I said that correctly, asks, injection of cold fluid into a hot reservoir incurs risk of thermal fracking. How do you see that risk impacting the integrity of your wells?
Yeah, we have actually done, but already, I think it was in 2020, we had a master thesis on that aspect. And what we see is actually that it is a slow process. I mean, for sure at the beginning, so the risk is on the first couple of hours or weeks, and then it's stabilized. So for me, it's not such a big concern. Then the question, of course, will be on the laterals here. If we are open loop, and it will be a question, I guess, on rock strength. And this we need to learn. To be honest, I think we need to test and see how it's.
Okay.
How it goes. Yeah.
And I think there was a question from Khan earlier that said, are these wells needing a casing, especially at greater depths? You know, like what kind of contact with the reservoir is there?
So at the moment, we consider without casing. We hope it's doable without casing. So the injection production well, they are cased. But for the heat producing section, at the moment, we consider barefoot. And then again, we will have to see. It's the fact that we want to go without casing is for economical reasons, obviously. Yeah.
There was a gentleman some years ago that mentioned barefoot completions were a bit, how should I say, risky, right? And that ties into the next question from Hector, because, you know, Mother Nature will take the path of least resistance. And so he's asking, do the calculations on your slide 10, which is right here, assume that you get 100% of the fluid injected back? That is, that you can achieve a perfect seal between the original hole and the subsequent holes connected to it.
Yeah, so these numbers, they consider 100% of loop, but we have also evaluated with some degrees of losses. And I would say up to a few percentage losses is okay. You should not increase that number too much, but obviously also for environmental reasons. And this is where the composition of the fluid has an importance to make sure that you can seal the well.
Mm-hmm. Yeah, and I think the challenges also lie if you're injecting the fluid and you suddenly have a secondary mechanism, maybe that you didn't expect there, and you start seeing the percentage of losses increasing. So now the connection suffers from that. But I think that's a case specific thing. So
this is maybe one thing I can add on the design is that what also we wanted to make sure is that the injection point is as far as possible from the production point to avoid, in case we would have connectivity between the laterals, avoid shortcut, avoid to connect the cold with the hot. Mm-hmm. And this is, if you look at Ever Design, this is something that may be a problem in their design, because they have the production zone. I mean, the loop is going like this. So the production zone is on top of the injection zone. And if you create connectivity between the wells, you may have a shortcut. Yeah.
You meant when you say shortcut, you mean short circuiting, right?
Yeah, exactly. Yeah.
Okay.
Mm-hmm.
All right.
Yeah.
Then we have a question from Soraya. Sorry, go ahead.
Yeah, sorry. You will contaminate the cold section or the hot section by the cold section. This is what I mean.
Okay. So Soraya gets a little more into the techno-economics. She says, can you tell us a little more? I think you talked a little bit about it, that what would be your expected ROI? How do you achieve to reduce the cost in comparison to what a company like Ever is doing? There's a lot of questions in one question, so maybe it will be okay if you just give us a brief summary. What has the most impact on the cost, and especially the use of a service well to drill laterals in the earlier production allowed by the incremental construction of the different legs? So just I think overall, what are you looking at in your in economic model, the expected return on the investment, and maybe tied to that, I could add to it is how do you see, because you said earlier we're in a different type of energy, so we have to think differently, and that's really what it is, right? We're not, but how do you do that? How do you make these economic models work in a world where?
It's a good question, and this is why. So I will answer it a bit weird. This is why I have been working with people from the financial world, from political economy background. We have also people in Ebosis from the debt industry, the banking industry. At the moment, to my surprise, I would say they are not worried about the economics because the market is so big. So no matter what, if we succeed in making this work, so a functioning technology, the number will come. Then it's about the long-term conception. So when you talk about ROI, for me, these numbers, it's always so much correlated with other things that we are used to do in a given manner and that we need to change. I mean, we need to change the perspective of maximizing the profit. We also need to understand the value that the system is providing to society. Like I mentioned, stable energy price. Is it okay if energy is costing a little bit more, but the price is stable, there is no risk for fluctuations and so on? And so what I could give like a number is that we have calculated the levelized cost of energy on considering system with 80 years lifetime. And we arrive around 22 cents per kilowatt hour for the heating and 15 cents for electricity, because electricity generation comes in addition of heating generation. So a plant that will generate electricity is also a plant that is supplying district heating. So you can sell the heat twice. And this is more or less how it is built. If there are more specific questions, maybe Patrick Scherer can answer his. I see him right here, but I don't know if he's still online because he's the guy on that.
Gotcha. We might need a follow-up. We might need a follow-up event where we actually just focus on the economics of these geothermal projects.
Yeah,
would be nice. We are actually planning to have one in the Geothermal Transition Summit that is planned this year. I think it will be in Munich. This will be an occasion for Patrick to describe what we do on the economic.
Nice. Patrick, would you like to chime in with a comment?
Well, I just can make a brief comment because we are talking here about long-term energy infrastructure. Okay? And I think the high initial capital costs are really amortized over a long-term period. So, and we have taken very conservative assumptions for the moment as far as the installation costs are concerned. The feedback we get from experienced oil and gas drilling companies that it's not uncommon that after 5 or 10 installations, you can start seeing a cost decrease on the order of 30 to 40%. Okay, so these numbers will go down definitely. But today the sustained costs are very, very much in line with what we see in the current markets, you know. And I would say thanks, quote unquote, to the horrible war in Ukraine. Okay, Europe has had a very hard reset on the notion of cheap energy. And this is not going to disappear. Even when the war ends, this will have long-lasting effects, and because energy is at the core of our society, in our societies, including Switzerland and many other countries in Europe, are thinking about really having energy secured as much as they can by reducing their dependence. And it's not an easy equation. And I believe really that deep geothermal is a very significant tool in making our societies more resilient. So on the cost side, again, this is absolutely sustainable, provided you have an asset class which is long-term oriented. This is not a 5-year or 10 years or 15 years project. This is 25 years and plus, right? So the EVOR assumptions, as far as I understand them, are built over a 30 years 30 lifetime. Okay, here we are talking about 60, 80, or 100 years. Okay? So this is it's clear there will be maintenance challenges and so on, but it seems, and it is, easier to mine a heat under our feet than to do space mining on the moon. No, okay, that's all what I can say for today.
I like that closing out. Thank you, Patrick. We might reach out in the near future to talk about that. I will say that we will tackle a couple more questions, Naomi. I think we're way past what our timeline is. But then again, I'm sure we will reconnect through the year to answer a couple more questions. There was one that asked, where exactly in Norway would the plan be? If that's disposable.
We have started discussions in Svalbard. And because there is the political situation over there that they want to decommission completely their coal-fired plant, and geothermal is an option. They already have like 2 projects. I would say I can show the kind of these kind of AGS on the table, and we are trying to discuss if an advanced geothermal system of our kind would be welcomed. This is discussion in progress. We've had a presentation in Norway. It was, I think, in March, also available on the internet in YouTube. If you want to see it, but yeah, in Svalbard. So remote place where it makes a lot of sense because they make use of the heat during the whole year. I mean, they need the heat every single day of the year. And this could be a very nice showcase for geothermal.
Okay, some people are saying that's a little too north, but we'll stay away from geographical preferences for now. There was a question from Regis that asked, are you in relation with AEGIS at ETH in Zurich?
Yes, so long story, a very long story. Yes, for sure, we have been in connections with AEGIS, actually also having discussions because the company behind AEGIS is developing, I can show you the one, it's the plasma pulse drilling.
Oh.
And so we are connected. It's about, I would say, human resources management. So to see how we can really align, we have exactly the same vision, and it makes a lot of sense to work together because we are 2 entities developing more or less the same thing in Switzerland. And so the answer is yes, we talk with them, but we are formally not linked to them.
Got it. Thank you so much. And I echo that message that you said about collaboration. I think that is really the key. Maybe that's what we didn't manage in the past to do best is talking to each other more. How do we maximize value without the whole we are competing, for something rather than let's work together to develop it further. So that's really nice to see.
Yeah, thank you so much.
There was you did get a lot of compliments, by the way, in the chat box. There was one question from Hernan that I find very interesting. We should tackle. It says there's been some work in terms of repurposing, but have you considered using a pre-existing depleted, let's say, oil and gas production or injection wells instead of drilling a new one, right? Depending on whether the conditions are favorable, like for a test.
So we have been considering using existing wells in Switzerland. So we have very early stage discussions, but one idea could be to reuse the well in St. Gallen because it's still open. There is a well in Basel also that is still open, but there the situation I would say is maybe more difficult. And what we consider very seriously is being the B plan, so the contingency for dry wells. When you have a hydrothermal project and they don't find the connectivities, they don't find the permeability, is to say, yeah, well, we are here. You already know the underground, you have done all the geophysics, let's go for a closed loop. And this is something that we consider very much.
Nice. That's actually pretty great. You're just gonna have to plan ahead for the completion and all, but that's great. It's you go for a certain source. Let's say you quotes fail and you don't manage, then you have a backup that will take over, minimize the footprint of surface, all that comes with it. So that was great. I will say that this was one of the best Q&As until now. Very good questions, great presentation. One thing that we will do is we will plan a presentation on techno-economics of geothermal. I think it's very important nowadays. We always hear about it. We don't really understand. When I say we, I mean generally. Obviously, there's people that are passionate about it, like Patrick. But I would like to mention that our next talk next month is going to focus on dynamic measurements in geothermal wells using a multi-sensor approach. We will continue these talks. I would personally like to thank everybody. I would like to thank you, Naomi, for being available, taking the time, and for presenting this in such a way that you really want to make the audience go out there, look for closed loop, get more educated.
Sure.
Really appreciate it.
You can share I will send you the PDF. You can share it for sure.
Exactly. So if you're okay, we will share the PDF version and this recording to all the participants. Obviously, they might reach out to you one way or another with questions and all, but that's the point of all of this. So thank you again.
Thank you so much.
Thank you all. Thank you.
Thank you.
That's